Welcome to Physical Hydrology Lecture 13, Part 1 on surface water. In this lecture, we will discuss the drainage basin processes that deliver water rapidly to the stream, contributing to the so-called quick flow volume of a stream, discuss the hydrograph, which is a graph of the changes in discharge with time, analyze the falling limb of the hydrograph of a storm event, so-called recession analysis, and separate the hydrograph into quick flow and base flow, so-called hydrograph separation. Let's start with the drainage basin processes that deliver water rapidly to the stream in humid areas. We will start with groundwater flow. In sloping terrain in humid areas, rainfall events have been observed to raise the shallow water table bordering the stream above the water level of the stream, causing groundwater flow to contribute to the stream flow. Also, during rainfall events in parts of the Netherlands with shallow water tables, groundwater may be transported rapidly through drains and ditches if these are deep enough to cut the rising water table. When a coarse textured layer with a high hydraulic conductivity overlies a fine textured layer with lower hydraulic conductivity, the percolation capacity, which is the maximum rate at which water can percolate through a soil, is initially controlled by the coarse textured layer. However, when the wetting front reaches the fine textured layer, the percolation capacity will be controlled by the fine textured layer and will drop sharply. If percolation continues, a purged water table may develop in the coarse soil above the impeding layer, which in sloping terrain may result in through flow, subsurface soil water flow parallel to the land surface in the direction of the stream or watercourse. If the quantity or volume of rain in millimeter causes the storage level in millimeter to increase and then to exceed the water storage capacity of the soil in millimeter, water is forced to the surface. Where such a purged water table cuts a sloping land surface, water will flow over the land surface as overland flow. Because the overland flow stems from the upper soil profile being saturated, overland flow produced this way is called saturation excess overland flow, or in short, saturation overland flow, in Dutch, verzadigingsoverland flow. Saturation excess overland flow is sometimes referred to as Dunnian overland flow, after Thomas Dunn, professor in geomorphology and hydrology. This type of overland flow is fundamentally different from an earlier discussed type of overland flow, where the rainfall intensity in millimeter per hour exceeds the soil's infiltration rate in millimeter per hour, as can be observed on bare or crusted surfaces with reduced infiltration under arid or semi-arid climates. This type of overland flow is called infiltration excess overland flow or Hortonian overland flow, after the earlier mentioned American ecologist and soil scientist Robert E. Horton. Macropores are pores with a diameter larger than 30 micron and relate to porosity around soil aggregates. A special type of both through flow and macropore flow is pipe flow. Pipe flow is rapid through flow bypassing the soil matrix, for instance, when water flows through burrows made by moles or voles, or when it flows through artificial drains. Soil pipes are a special type of macropore, as they are continuous and prolonged in one direction, parallel to the land surface. During wet conditions, natural soil pipes, mole and vole burrows, may rapidly transport water parallel to the land surface in the direction of streams. During dry conditions, natural soil pipes located near the land surface and above the water table contain little or no water. Water can only enter a soil pipe from its surrounding soil matrix if in the matrix a critical threshold suction related to the natural soil pipe's diameter is reached. As the natural soil pipe's diameter of a mole or vole burrow is in the order of 1 to 2 centimeter, the matrix threshold suction must be almost 0 centimeter, meaning that the surrounding matrix must be near saturated. Similarly, artificial drainage pipes, for instance used to drain cultivated land, are only effective when the soil matrix is near saturated or when the water table rises to the level of the drainage pipe. This sheet shows a schematic presentation of two different ways for the occurrence of pipe flow. The illustration to the left shows the situation where water is fed to a pipe from a perched groundwater body that has developed above an impeding layer. This is the situation where water is fed to a pipe from a near or fully saturated soil matrix next to the pipe. The illustration to the right, on the other hand, shows a situation where pipe flow develops under dry circumstances. In soils prone to seasonal shrink-swell, such as clay soils, the occurrence of dry circumstances, or thaw after a freezing period, can cause shrinkage cracks to open. If the shrinkage cracks are deep enough and connect with the pipes, a very rapid short-circuiting of rainfall via shrinkage cracks and pipes to a downslope stream can evolve. As an example, soils in forested areas of the Steinmergelkeuper Marls in the Goodland of Luxembourg are made up of a 30 cm thick loam-textured layer overlying an impeding clay horizon. The topsoil above the impeding layer contains many mole burrows that are interconnected in a downslope direction for observed lengths of up to 120 meters, and that support the short-circuiting action just described during a large part of the year when shrinkage cracks are open, as shown here, and connected with these natural pipes. Water has been observed to gush out of pipe openings at downslope near stream positions in these forests during many storm events in the area, and subsurface flow through the pipes was observed as turbulent and erosive, further enhancing its short-circuiting action. One such pipe opening is indicated on this photo. The area of sedimentation on leaves lying on the forest floor from water that has gushed out of this pipe opening is clearly visible as a darker area on the photo. Shrinking and swelling of clay is a seasonal phenomenon, and interestingly, for every dry period, these shrinkage cracks in the Steinmergelkeuper Marls of Luxembourg can be observed to reappear at the exact same spot as before. Similarly, subsurface flow through artificial drainage pipes in a clay soil in Oxfordshire, England, was found by Robinson and Bevan to be more responsive to storms in summer than winter, also because in summer the soil was dry and cracked. The relative importance of matrix flow and macropore flow generally depends on rainfall intensity and duration, infiltration capacity of the matrix, the shape and connectivity of pores, and the wetness of an area prior to rainfall, the so-called antecedent moisture content, but is also linked to topographical position in the landscape and vegetation. This sheet shows principal locations of flow convergence in drainage basins. Infiltration into a layered soil may lead to the development of a perched water table. Importantly for humid climates, when the perched water table reaches the land surface, any extra rain that falls will immediately become saturation excess overland flow, which is transported over land and thus rapidly to the stream, contributing to the quick flow of the stream. Topographic convergence zones can be hill slope hollows or topographic depressions, that is, slope concavities in plan or slope concavities in section, as shown in this figure under A and B. For both types of concavity, through flow can enter such a concavity more rapidly than it can leave downslope, thereby forcing water to the surface. Also, where an upper layer in the soil that supports through flow becomes thinner, a perched water table may develop and rise to the land surface, as shown under C. A perched water table and through flow may also develop as the result of the reducing hydraulic gradient as water moves downward through a soil, even a relatively uniform one. This may cause the development of a saturated layer at some depth in the soil profile, as shown under D. In conclusion, the process of a rising water table reaching the land surface is a very important mechanism for the generation of saturation excess overland flow in humid climates. The saturated areas where quick flow is generated, with saturation often occurring from below as just explained, are called variable source areas or partial areas. This figure provides a summary of the Hewlett hypothesis of runoff formation in humid climates as presented by Ward and Robinson. Figure A shows that water infiltrates the slope surface and moves as through flow, that is, matrix flow and/or macropore flow under the slope surface. Figure B shows that convergence and infiltration in the lower slope areas leads to surface saturation and groundwater recharge, which will create both an overland flow and a groundwater flow contribution to the stream, with the groundwater ridge expanding in some locations into a wider area of surface saturation as shown in figure C. This figure shows that the areas that become saturated from below expand upslope and upstream if rainfall continues. This phenomenon has been observed in situ as well as through remote sensing techniques. These saturated areas that contribute to quick flow can expand and contract in size between storms and during the course of a single storm. They are called variable source areas. Source areas with as adjective variable because of its expanding and contracting nature. Often, but not necessarily so, variable source areas are located near the channel network that drains the area. The latter has to do with processes such as colluviation, the deposition of sediment through the action of gravity at the foot of a slope, causing the hill slope angle to diminish in the direction of the stream, and alluviation, the deposition of sediment by streams, causing areas near the stream to be flat, that is, when viewed in cross-section. These flat areas are called alluvial terraces, and their slope logically is parallel to the former stream's gradient. Thus, processes such as colluviation and alluviation are responsible for having flattened and/or flattening the foot of hill slopes, and thus for topographic convergence that amplifies the effect of a rising water table and may cause through flow to exfiltrate. This sheet shows the earlier presented drainage basin hydrological system, but now with the processes between the main water compartments discussed at this and preceding lectures more prominently included. This figure shows a hydrograph, a graph of the changes in discharge along the vertical axis with time along the horizontal axis for a precipitation event, together with the number of hydrological terms used to describe a hydrograph. The discharge, or part of the discharge, of a stream caused by processes delivering water rapidly to the stream is called quick flow. For the discharge volume that stems from these rapid processes, we use the term quick flow volume. During periods with no precipitation, many streams, especially in humid areas, continue to carry water. The streams are fed by processes such as sustained groundwater flow and slow through flow through the soil matrix from an earlier precipitation event or events. The discharge or part of the discharge of a stream caused by processes delivering water slowly to the stream is called base flow. For the related discharge volume, we use the term base flow volume. The rising limb is part of the hydrograph with increasing discharge before the hydrograph has reached its peak, the peak being the maximum discharge during a precipitation event. The falling limb is part of the hydrograph with decreasing discharge after the hydrograph has reached its peak. The term recession curve is synonymous to the falling limb. The quick flow recession is part of the hydrograph with gradually declining quick flow. The base flow recession is part of the hydrograph with gradually declining base flow. Separation point is the point on the recession curve that separates the quick flow recession from the base flow recession. Inflection point is the separation point determined by assuming that the recession curve can be modeled as the discharge from linear reservoirs that represent quick flow and base flow. More on this shortly. Finally, the time of concentration is the time required for surface water or other water contributing to the quick flow of a stream to flow from the farthest point in the watershed to the outlet. Streams that hold water throughout the year are called perennial, whereas a channel that only holds water during and immediately after a rain or snowmelt event is called ephemeral. An ephemeral stream thus has no base flow, only quick flow. This sheet shows a hydrograph of heavy rain on a wadi, a usually dry riverbed in a semi-arid climate with the exception of periods during and shortly after heavy rainfall. A wadi thus is a type of ephemeral stream and its discharge is made up solely of quick flow. For an ephemeral stream, the recession curve can conceptually be interpreted as outflow from a quick flow reservoir. The recession curve can mathematically be described as an exponential decrease starting at the hydrograph peak, as shown here. Qt is discharge at time t after the start of the recession in cubic meter per second. Q0 is discharge at the start of the recession in cubic meter per second, thus at the hydrograph peak. T is 0 seconds. E is the base of natural logarithms, 2.71, etc. Alpha is the recession constant per day, and T is time in days. In analogy with the Horton equation for ponded infiltration, the equation can be rewritten for small constant time intervals delta t as shown here and here. Remarks made for the decay constant alpha when introducing the Horton equation for ponded infiltration similarly hold for the recession constant alpha in these equations. E to the power minus alpha delta t is smaller than 1. Also, if the recession constant alpha is large, the recession curve shows a steep decline and the depletion of the reservoir is fast. Consequently, if alpha is small, the recession curve shows a slight decline and the depletion of the reservoir is slow. Alpha ranges from 1,000th per day for deep groundwater to over 3 per day for overland flow. The equation can be rewritten in semi-logarithmic form as shown here. This equation plots as a straight line in a graph with ln qt on the vertical axis and t on the horizontal axis, and the value of alpha can simply be determined as the absolute value of the slope of this straight line. This sheet shows the hydrograph of a perennial stream, for instance, a stream in a humid climate setting. The discharge of the perennial stream is made up of both quick flow and base flow. The recession curve of the hydrograph shown here can conceptually be interpreted as outflow from both a quick flow reservoir and a base flow reservoir, with the larger outflow per unit of time from the quick flow reservoir. At the separation point, the quick flow reservoir has emptied, and from then on there is only outflow from the base flow reservoir. As the outflow from the quick flow reservoir is dominant, the first part of the recession curve after the hydrograph peak can simply be interpreted as outflow from the quick flow reservoir alone. The recession curve can therefore mathematically be described as first an exponential decreasing outflow from the quick flow reservoir, and then after the separation point an exponentially decreasing outflow from the base flow reservoir. For both parts of the recession, the just discussed equations can be used, be it with a different value of the recession constant alpha for the quick flow and base flow reservoir. Note that the quick flow reservoir has been drawn with a larger opening at the bottom than the base flow reservoir. The size of the opening and the friction are incorporated in the value of the recession constant alpha, alpha being largest for the quick flow reservoir with its fast depletion. The figure shows a base flow separation line obtained using the constant slope inflection point method. The position of the inflection point is found as the point in time where the slope of the semi-logarithmic plot of ln qt versus t changes. The method has been extensively used by me when comparing hydrographs of brooks in small 1 to 2 square kilometer forested and grassland drainage basins in the Keupermaals of Luxembourg. Because usually more than one inflection point is found on a recession curve, I use the inflection point with the lowest discharge as the selected inflection point to distinguish between quick flow and base flow. There are many methods for hydrograph separation into quick flow and base flow. All methods have in common that they are unavoidably arbitrary. Importantly, one should always stick to the method one sets off with when analyzing hydrographs, or else the comparison basis is lost. For all methods, the area under the hydrograph curve but above the baseflow separation line or curve gives the quick flow volume during the precipitation event in cubic meter, whereas the area under the separation line or curve gives the baseflow volume in cubic meter. There are many methods of hydrograph separation. This sheet shows 3 graphical methods. The constant discharge method A assumes that base flow during a precipitation event is constant and equal to the discharge level at the start of the precipitation event. A large disadvantage of this method is that the discharge may not return to this starting level because of the start of a new precipitation event. The constant slope inflection point method B, used by me, assumes an immediate response in base flow to precipitation and connects the start of the rising limb with the inflection point on the recession curve. The concave slope inflection point method C assumes a continued decrease in base flow during the rising limb of the hydrograph and projects the declining antecedent baseflow recession prior to the precipitation event to directly under the hydrograph peak. The minimum obtained this way is then connected to the lowest inflection point on the recession curve. Similar to precipitation depth and evaporation, the discharge volume of a river may be presented as a length unit, for instance, millimeter. Discharge volumes in cubic meter can simply be converted to meter by dividing by the total drainage basin area in square meter. Multiplying this result by 1000 millimeter per meter, of course, delivers an answer in millimeter. One should divide by the total drainage area, irrespective of the fact whether all or only part of the drainage basin actually contributes to the discharge. This is because the same total drainage basin area is involved when translating precipitation or evaporation from volume units to length units or vice versa. Importantly thus, a discharge presented for instance in millimeter per hour is not a velocity, what it may seem at the first glance, but a discharge in cubic meter per hour adjusted for the drainage basin area by dividing by the total drainage basin area in square meter and multiplying by 1000 millimeter per meter. The runoff coefficient of a stream can simply be determined by dividing the discharge volume in millimeter by the received precipitation volume or precipitation depth in millimeter and then multiplying by 100 to convert from fraction to percentage. The term runoff and runoff coefficient should be taken as the discharge of a stream. Another use of the term runoff is as a synonym for overland flow. Please note, the runoff coefficient on an annual basis is defined as the total discharge volume in millimeter or cubic meter as a percentage of the precipitation volume in millimeter or cubic meter on an annual basis, whereas the runoff coefficient on a storm basis is defined as only the quick flow volume in millimeter or cubic meter as a percentage of the precipitation volume in millimeter or cubic meter on a storm basis. Usually in plots of storm hydrographs, discharge and precipitation are presented using different units. For instance, cubic meter per second for discharge versus millimeter per hour for precipitation, and thus along differently scaled axes. The first impression of such figures may be that a large percentage of precipitation is discharged as quick flow during storms, which may be misleading. As often runoff coefficients on a storm basis are surprisingly low, as interception and evaporation losses and storages at the surface and in the subsurface usually are quite high. However, in situations when a small clayey drainage basin is pre-wetted by earlier precipitation, or when rain falls on a frozen soil, or when snow melts, storms with a high runoff coefficient may occur. To get the perception right, the figure to the right shows a hydrograph of quick flow for a storm with a runoff coefficient of 30% with, just for once, precipitation and quick flow presented in millimeter per hour, thus along equally scaled axes. Part 2 of this lecture will be on hydrological simulation models.